Now, we're going to jump ahead a bit because we've learned quite a bit about atoms since then to 1981 when scientists came up with the first microscope that could actually see atoms. And here is an early picture of some carbon atoms, and they look a lot like Democritus predicted they would, like solid little spheres all in a row. Look at that. They're all packed in there. Now, these aren't, of course, exactly what atoms look like. These are really the electron cloud, in a sense, that the microscope is picking up with its instrumentation. But these are actual atoms and how they're arranged. And throughout that decade, we got better and better about actually being able to use nanotechnology. In other words, working with extremely small things like atoms themselves. IBM created the world's smallest logo written in atoms of the element xenon. And these are individual atoms that actually make up this logo. And they were able to manipulate those into just the right arrangement. Pretty amazing. We're getting pictures now of actual molecules. These are individual atoms that make up a molecular chain here. And and now we're at the point where just recently in the last several years we've got these massive particle colliders. This one here just came online finally in 2008 was when it first really fired up and started going. And this one's in Switzerland and France. The border runs right down the middle. It's this massive, in fact, probably the world's largest scientific instrument yet built. It took 10,000 scientists roughly many, many years to actually design and construct this thing. And it's an underground tunnel with this huge radius miles across, as you can see. And underground here, in this tunnel, is this tube where particles are accelerated, and they go around and around and around this racetrack, in a sense, incredibly fast, at 99.99999% of the speed of light. And the idea then is to collide these particles with another particle, with another particle going around the other way at nearly the same speed. And they collide these things in these massive detectors that then can detect what happens when the collision happens. And this, I mean, look at the size of this thing. This is one of the detectors that measures these collisions. I mean, these things are massive. Here's a dude right here. I mean, these things are incredibly huge and complex. And what they're able to do is as atoms and particles collide together, they can then look at what comes flying off. They look at the debris, essentially. And they can find all kinds of things like neutrinos and muons and gluons. And they've been looking for the Higgs boson, for instance, which they finally found here just in the last year or so. And by looking at the trails of these bits of debris, scientists who are way smarter than I am can figure out what they're made out of, and exactly how they behave, and start to figure out not only what protons and neutrons are made of, but also electrons and all kinds of other subatomic particles. And these here are the results of literally billions of collisions between particles. And by interpreting these diagrams of what happens when these things collide, we're able to get a pretty accurate picture of what's going on inside of an atom. And here are all these different types of subatomic particles. The ones in purple here, the quarks, are the ones that make up protons and neutrons. Put these together, you get protons and neutrons. Here's an electron. Electron down here. You've got other little particles called neutrinos, and bosons and gluons and photons. All kinds of incredibly complicated particle physics that is taking us into a new century, and we've come a long, long way, and are getting a much more accurate picture of what an atom really is and how it really behaves. Fascinating stuff. The big picture is that we've come a long way. You don't need to remember exact dates. You don't need to remember names necessarily, other than the fact that we've used a lot of experimental evidence to try and come up with a more accurate picture of what an atom, which is incredibly small, really looks and acts like, and why.